Welcome back, everybody. So today we're going to talk about Faraday's law. And Faraday's law is basically talking about how you can induce a current in a conductor by moving these charges through a magnetic field. And this is not new to us. We've talked about that before. Remember, IB fine. If I have a current and I have a magnetic field, then there's always going to be a force that's applied to those charges. Now, the only part that confuses people about this is we're going to move those charges through the magnetic field. That's going to be our current. The charges then are going to feel a force, which is going to cause them to move in a direction perpendicular to both of these. So if those charges are moving, that is an additional current to the current that we applied, that we forced them to move as they went through. And so it's that additional current that we refer to as an induced current. So don't get confused. We're talking about two separate currents. We've got the current that's due to my moving those charges through the magnetic field, but then that's going to cause them to move in a different direction. And a moving charge is always a current. So keep that in mind as we look at the implications of Faraday's law and how we can use that. Okay, let's get started. All right, so take a look at the diagram here. We have a magnetic field that is coming out of the page. Those are the little circles that we've drawn here. And then I have a conducting bar that we're dragging through the magnetic field to the right there. Now, this bar isn't connected to a battery. There's no circuit. There's no nothing. So there's no net charge on it. But think all the way back to the beginning of the semester. There is still positive and negative charges in there. They're just randomly mixed up, and so there's no net charge. So as I draw that bar across, what's going to happen to those positive and negative charges? Pause the video, think about it, see if you can figure out how they're going to move. Well, we figured this out using our right-hand rule number 2, our IB fine. I is the current. Now, like we said at the beginning, there are actually two currents going on here. This current is always the current that I personally am applying to it. So that's that velocity as I drag them across the page. They will feel a force that's going to be in a direction perpendicular to these two, and that force is going to cause a movement, which is a current. That's the induced current. We haven't talked about that yet. So the current then that I'm applying is going to be to the right. The magnetic field is out of the page, and so my positive charges then are going to feel a force downward. And so all my positive charges are going to start to collect down here at the bottom. Similarly, the negative charges are going to feel an upward force due to the magnetic field, and they're going to start to collect up at the top. So those charges then, as I move the bar through the magnetic field, it causes those charges to separate. Well, let's see what happens to the electric force that's going on between them. So the question says, what is the direction of the electrical force applied to the positive charges? So remember, I've got positive charges on the bottom, I've got negative charges on the top. We're talking about the electric force, not the magnetic force. Well, they're attracting each other, right? So that electric force then is going to cause those positive charges to want to move upward. The magnetic force is pushing them down. The electric force is pushing them up. Similarly, let's think about the negative charges. Which direction do they want to go? Well, they're still being attracted, so they're going to want to go downward. Now, before I started moving them, they were all mixed up. So there was no electric force. There was nothing that would cause them to attract each other or anything like that. As I applied that magnetic force, then they started to separate. Initially, there was a very small electric force. Wasn't enough to overcome the magnetic force. So, but as I get more and more charges separated, then that electric force between them is going to increase. So will the charges continue to separate? No, at some point, they're going to have to be exactly equal because the magnetic force is constant as I'm pulling through here. But that electric force is getting stronger and stronger and stronger as I separate out the charges. Eventually, they're going to separate or they're going to be equal. And so then the system will be in equilibrium. Okay, so let's see what's going to happen when I have a loop of charges. So now I still don't have a battery, but I'm going to have a current. So let's delete this page here and look over on the next page. So now it's just a loop of conducting wire. That's it. So there's no battery, but I'm going to take that and I'm going to move them through I'm going to move that loop through this magnetic field. Initially, I'm completely outside of the magnetic field. This is a very, very important exercise for you to understand what's going on. So seriously pause the video on this one. And what I want you to do is I want you to draw the direction of the force on the charges. Now remember that that force is causing the charges to move in a direction perpendicular to my current, the current that I put on them, the real current, and the magnetic field. So this force then is causing an induced current because it's causing those charges to move. So we're talking about this smaller secondary current that's going on. All right, pause the video, and for each one of these four segments, I want you to tell me, is the force, what is the direction of the force, if any? Is it to the left, to the right, up, down? If it's nothing, go ahead and write a 0. Pause the video, do that. That should take you a few minutes. Use your right-hand rule and figure it out. Okay, hopefully you didn't just wait for me to do this, because you aren't going to understand this kind of confusing difference between a regular current and an induced current if you don't do this. All right, so looking at our first case then, do I have any magnetic force at all? No, right? I'm not inside the magnetic field, so it's going to be 0 on all sides here. Now, once I start to move it into the magnetic field here, what direction of the force I'm going to feel? Okay, over here, this is the easy one. It's not in the magnetic field, so it's still going to be 0. All these are zeros. Let's look at this one right here that's completely inside. Well, this is the same case that we had before. We said that all of the positive charges then are going to move down. So I'm going to get this induced current moving the positive charges down through the wire. How about on the sides here? Well, don't get confused. Use that right-hand rule. I'm still going to get a force acting down. Now, you may think, okay, well, why doesn't this make the whole wire move through? Well, it's a thin wire, and so the charges are going to move in the wire, but they're not going to be able to move the wire itself. That's what we're assuming, is that I'm pulling that through. They're not going to make the wire move. The charges can't, bump up against themselves and cause it to move. So we're going to consider this to be a very thin wire. So what's going to happen is your positive charges are going to collect on the bottom side of that wire. It's not going to be enough that you can tell a difference because it's a very, very thin wire. So we can effectively ignore any induced current that's produced here because it's not traveling along the wire. Remember, we've always considered our wires to be infinitely thin, just very, very thin. So since there's no current traveling across the wires, they're just going to go to the bottom. They're going to stay there. And that's going to be the end of it. And it's going to be more like the initial case that we had. All right, now let's look at this third one here. Well, it's the same thing. In all cases, then, I'm going to have all of my charges are going to be all my positive charges are going to be moving down. So I'm going to get an induced current where everything's moving down. In this case, all my positive charges will go here. All my positive charges will go down here. Looking at this case, then, this one's obviously 0. And again, it's going to be down. So don't overthink this. It should be obvious what's going on. It's always going to be that downward force, just like when I was moving the wire through. And then, of course, once I'm completely outside of the magnetic field, I'm not going to see any forces at all. This is going to be important because we're going to see that in certain cases, I'm going to build up a current that exists going through the loop. So take a look at the next microtask here. And I'm just going to briefly slide this one to the side here. What is the direction of the current if there is no magnetic field inside the loop? Let's zoom over to where we can see both of these. So if there is no magnetic field inside the loop, so this is the far case that we're talking about over here. Well, there's no current, right? There's no force being applied to it. What is the direction of the current if the magnetic field inside the loop is increasing? So that's this case right here. And you may say, well, I don't know, it's just moving down. But remember, all of these wires are conductors. So let's use a different color here. So as I get charges that are forced downward, they will actually continue on around the corner here. And then you would think, well, why would they be going up? Well, that's because these charges over here are pushing them. And so as they continually push, then they continue on around the loop like this. That's the key point. Make sure that that makes sense to you. So what's going to happen then is I'm going to get a current that's going to be induced clockwise around the loop. So as the amount of magnetic field inside the loop increases, it's going to go clockwise. So in this next case then, when the magnetic field inside the loop is constant, so you see that even though I'm moving, the amount of magnetic field contained inside that loop doesn't change. What is the current in this case? Well, this might be a little bit tricky, but let's think about it. I've got a current moving down this way, so it's trying to push those charges this way, and this is trying to also push those charges this way. I actually have a force acting on it in this case. So I've got a force here and a force here. And so they end up simply coming together and they form an equilibrium with that. And so the end result then is I'm not going to get any current at all. And you see why. In this case, in the first case, I was able to just let it go all the way around like this because there was nothing stopping them. In this case, though, I've got basically a current this way and a current this way, and they're going to cancel each other out because they're going to hit an equilibrium. All right, now let's look at the last case here. So in this case, then, I've got a current going down this way. And remember, these two up here and down here, they're not going to affect anything because they're not traveling along the wire. So it would continue on around the loop like this. So what direction is the magnetic field? Well, I'm sorry, the current. It's going to be counterclockwise in that point. So the important thing that we're seeing here is that it's not enough to simply have a loop in a magnetic field. That's not going to induce a current. What I have to have is I have to have the amount of magnetic field has to be changing. If I'm completely outside, I'm completely inside of this constant magnetic field, I get no current whatsoever. But if it's changing, then I'm going to generate a current. And the amount of current that I get depends upon the sign of it, clockwise or counterclockwise, depends upon whether that amount of magnetic field is increasing or if it's decreasing. So this leads to Faraday's law. And let me get my mouse where I can zoom in on this. Here we go. So a changing magnetic flux through a conducting loop induces a current in that loop. And so we haven't used this term flux with magnetism yet, but it's exactly the same as with the electric flux. And that's what we're showing over here. The magnetic flux is simply the integral of B dA. So I take all of this area for this particular surface that I have, and the amount of magnetic field that's moving through that surface. Don't get confused. This is not an Amperian loop. This is actually an actual surface. You can kind of think of it as a Gaussian surface. But so the amount of flux that's moving through there is going to be, if that's changing, that's what's going to induce our current. Now, I want to pause and make sure that nobody's getting confused, because didn't we just spend a whole lot of time saying, oh, well, you can't use the Gaussian surface with this? Well, no, we can. Remember that this is not Gauss's law, even for electric. This is simply the definition of flux. And we'd found before that the electric flux was equal to this constant Q enclosed divided by epsilon naught. However, for the magnetic flux, which is what we've got right here, that quantity is simply equal to zero. But the quantity exists. So if it's changing, that's what Faraday's law is looking at. So if the amount of flux is changing, then that's going to give us something that we can use. So we make the note here. Faraday actually defined this in terms of an EMF, an electromotive force. And that's kind of a really poor name. Faraday didn't really know what it was that was pushing these currents around, that was pushing these charges around. So he referred to it as an electromotive force. We now know that it's not a force that's making things go, it's a voltage. Remember, a potential difference. That's what causes a current to form. And that's simply nothing more than Ohm's law, right? So if I have a potential difference, that's going to give me a current. And the amount of current I get depends upon the resistance. That's constant of proportionality. So that's V equals IR. So an EMF is actually simply just a voltage. And you will see a lot of engineers as well as scientists, physicists will use this term right here, this symbol here to represent an EMF. And usually they'll use it to distinguish it from a battery. So they'll say, well, okay, this is an EMF that's induced. It's a voltage that's induced as a result. But don't get confused. It's measured in volts, and it is a freaking voltage from that. It's just not a voltage that's being provided by the battery. That said, there's nothing wrong with using this symbol to represent the voltage produced by a battery as well. The battery, you could say, is producing an EMF, and that's what's causing things to move. So it's really more about historical purposes than anything else. Don't get confused. You can use them interchangeably, but you should be able to recognize both of them. The way I think about it when I see that EMF symbol is I just think voltage. As long as you think voltage, it's got units of volts, everything's going to be fine. So Faraday stated his law in terms of an induced current. But remember that current's very difficult to measure, but it is also proportional to the voltage, the EMF that is being produced. And all I need to know for that is the resistance, and I could get it. So this statement of Faraday's law is absolutely equivalent. And you should be able to see that because it's just Ohm's law that's coming into play. So you can think of it in either direction. You can have, if I have a changing magnetic flux, has to be changing, then I can get a current through the loop, or equivalently, I can say that there is a voltage that's being produced. The voltage part is important because that's what leads to our electric generator from that. So let's finish up our microtask here. It says, if the magnetic field inside the loop, let's go back to where we can see our picture. So if the magnetic field inside the loop is constant, do I get any kind of a current? And no, we don't, remember, because it has to be changing. So in that case, it's going to be 0. However, if it's decreasing then, again, zooming back out so that you can see, you see that now it goes counterclockwise. So the amount of current and the direction of the current that I get is going to depend upon whether that loop, the flux inside that loop, is increasing or it's decreasing. So when we've been talking about our flux, then we're talking about the flux that's going through this surface defined by the loop. So if you think about that plane of surface as some sort of membrane and the amount of magnetic flux going through there. So as that magnetic field goes through there and increases or decreasing, that's what's going to produce our current. All right, let's look over on the next page and go and get rid of these 2 pages. And we'll erase this so that we've got something neat to work with. There we go. All right, so we need some sort of mathematical expression, as always, for working with this. We've talked about a qualitative thing, and what we've said is that the EMF, and you can use this symbol if you want, depends upon a change in the magnetic flux. And let's go back to pen. This is the symbol that we use for our magnetic flux, that Greek letter with the little m there. So go ahead and very quickly write yourself an expression for Faraday's law in terms of symbols. Don't overthink it. It's actually very simple. Sure. So this is my induced EMF, and that's going to equal to the change in the magnetic flux in a certain amount of time. So we could do this as an average with deltas with calculus-based class, so we'll go ahead and use differentials for that. Now, there is one other thing that we need to know. What is the sign of this? And we've seen that as it's increasing, the flux is going to be clockwise. As it's decreasing, the flux or the current is going to be counterclockwise. But we need to get a sign somehow from this. And so how do I figure out, is this going to be positive or negative? How do I figure out that direction of that change from this? So you can see that if the flux is decreasing, then that's going to be negative. But what does that mean exactly? So let's see if we can come up with some arguments for why we might could figure that out. So that's what this next task is doing. All right, to start off with then, we've got a bar magnet that's going to be moving through the loop. What does the magnetic field of the bar magnet look like? Well, I've got a dipole, so it's going to go from north to south, or from south to north. this. So as it enters into the loop, then the direction of the magnetic field is going to be pointed down. As it approaches the loop, the magnetic field inside the loop is going to get stronger. So what's going to happen to the magnetic flux? Don't overthink it. Sure, it's going to increase because the magnetic field is increasing. I've got more of those field lines that are moving through the loop. And if you think about it, as I start to approach it, I get just a very few. And then as I get closer and closer and closer, I'm going to get more and more of these. So is a current, and again, therefore an EMF, induced in the loop as the magnet approaches? Why or why not? Well, sure it is, right? Because the amount of flux is changing. Therefore, there must be some sort of a current that's being induced in it. That's what Faraday's law says. Now, the question is which direction is it going to go? So let's suppose, and we're just guessing here, let's suppose that the induced current went clockwise around the loop. So as I'm looking from above, then we want the current to go clockwise around the loop like that. Use your right-hand rule number 1. What would be the direction of the magnetic field produced by that current? We're talking about inside the loop here. It's going to be up or is it going to be down? Well, you grab hold of the wire and you see that inside the loop, it's going to be down. Well, that's interesting. So the total magnetic field then, we've got the magnetic field due to the magnet, it's down. And as that magnet moves through, if this were true, then it would create another magnetic field that is also down. So what's going to happen to the total strength of the magnetic field if they're both down? Well, they're going to increase. So that means that I've got a change in that magnetic field. It's increasing. Well, if I have a change in the magnetic field, what must be produced according to Faraday's law? Well, I'm going to have to get more current. And so it's going to increase even more, which is going to increase the magnetic field even more, and so on and so on and so on. Well, what you've done here is you've created energy out of nothing. You've basically violated conservation of energy. It's one way that you could produce a perpetual motion machine. Simply by approaching the magnet into the coil, you're going to generate an infinite amount of current because it's going to keep getting bigger. It's going to be this feedback loop, bigger and bigger and bigger. Well, obviously that doesn't happen. So that tells us then that we must have it wrong, that it must not be going clockwise, because if it did, we would violate conservation of energy. This kind of thought experiment is very important when you're trying to do theoretical physics, is you want to think about, okay, what would happen? And if you don't know, you pick one. And then you see, okay, what would be the consequence of that? If everything works out, fine, tentatively, everything's fine. You start thinking of other cases. But as soon as you get one case that kind of makes it so that violates a law of physics, you go, oh, okay, it can't be that. In this case, we only had 2 choices, so it must be the other case. So let's go on to the next page here. So what direction would the current have to go in order to keep it from being a perpetual motion machine, in order to keep it from violating conservation of energy? Well, it has to be the opposite way. I must have had it backwards. So therefore, it must go counterclockwise in that case. And so this is called Lenz's law, after the Russian physicist who first came up with this. And it says the direction of the induced current always opposes the change in the flux that produces it. So what that means is that if I have an increasing flux, because, for example, my magnet is approaching the wire, then the induced current must be in a direction that would reduce that magnetic flux. So let's draw our loop here. So here's my loop, and here's my magnet coming down. And this is the north end. So if my current were going counterclockwise around, now you see, if you use your right-hand rule, you're going to see that inside the loop, the magnetic field that is due to the wire, due to the induced current wire, is now up. And so that is reducing the magnetic field of the magnet. And so therefore, I'm not getting something for nothing. I'm not violating conservation of energy. And so that must be the direction that the current has to be going. So simply by physical principles, we can predict how that's going to be. Okay. So then, if we want to write our final form then all we need to do then is put in a minus sign in there. So my EMF then is going to be minus my change in magnetic flux with respect to time. And this is the final form of Faraday's law. And you'll hear people refer to Lenz's law. Well, okay, there's not a separate equation for Lenz's law. Lenz's law is simply the minus sign in Faraday's law. It's saying that if the change is increasing, then the current must be such that it's going to reduce that change. And to do that, I need to have a minus sign in front of it. All right, so let's go back to our loops that we looked at before. So let's go ahead and delete this page. Based on what you know now, what direction is going to be the current, clockwise, counterclockwise, or zero, and what will be the sign of the EMF? Will it be positive, negative, or zero? Pause the video. Let's see if you can put it all together and see if you can figure it out. All right, so when I am outside of the magnetic field, is the magnetic field inside the loop changing? No. So obviously there's not going to be any current at all. And if there's no current, there's not going to be any voltage, no current, no EMF that's going to be produced. As I move in here, the current is the flux in here is going to be increasing. And so we saw that that's going to produce a force that's going to be down. And so my current is going to be clockwise. But the direction of my EMF then has to fight that, which tells me then that my EMF, my voltage, has to be negative that's going to be produced. Okay? If you're not sure about that, go through the logic and make sure that you can see how that would work. Use your right-hand rule and see if you can figure out how that goes. All right, now, once the magnetic field in here is constant, what's going to happen? Well, if there's no change, then there's not going to be any current, and therefore there's not going to be in any EMF. As I'm moving out, I still have that force that's downward, but now it's on the left side of the loop. And I don't have anything to counteract it. So my current then is going to be counterclockwise. And so the EMF is going to be in the positive direction from that. And then finally, once I'm completely out, I'm not going to have any current. It's going to be like this. So there's a good rule of thumb that's written down here for how to remember Lenz's law. So the induced current reinforces a decaying magnetic field and resists an increasing magnetic field. So it always works in the opposite direction. So we're talking about only what's inside the loop. And as you see, like in the example we have here, the amount of magnetic field, we're talking about this example that's currently visible, the amount of magnetic field here is decreasing inside the loop. And since that's increasing, then it's going to produce a current that's going to shore that up, that's going to try to reinforce it. Let's see if that makes sense. So I've got a current, for example, that's going down. So using my right-hand rule then, you see that now the induced magnetic field is going to be out of the page. It's going to try to reinforce that. So there's a number of applications with this, a number of very important applications. Probably one that all of you have in your homes is something called a ground fault interrupter. And let me zoom in on this picture right here. So in normal operation, the current is flowing in both directions through the two wires. So I've got opposite directions, so the current basically is going to cancel each other out from that. And so the net magnetic field is going to be zero. If you think about it, I've got one going this way and one going the other way. So they're going to cancel each other out. If there is a short, if one of those wires were to break, or be shorted out so that there wasn't any current going through here, then there wouldn't be any return current. At this point, all of a sudden, I'm going to go from, let's see if I can hold my hands backwards, I'm going to go from no magnetic field to very suddenly, I'm going to have a magnetic field only in one direction. That sudden change, remember, it's d phi dt. So that means that it's going to be an extremely large current that's going to be produced. And so the circuit breaker then trips because it gets a large current. That's how a circuit breaker works. When it exceeds the amount of current that the circuit breaker is rated for, it trips and it shuts everything down. Well, the amount of current that's going to be induced is going to be much larger than the current of the actual device that's here. So that's going to trip before any kind of strong current actually moves through the device that's shorted out. So if you've got, something gotten wet, water has shorted things out, then this will almost instantly break off the current. And so this keeps you from being electrocuted or starting a fire or something like that. So these GFIs, these ground fault interrupters, are a direct application of Faraday's law. Oh, one of the more important ones, though, if you ever decide that you're going to have kids, is a sleep apnea monitor. So this attaches around the baby's stomach. And as long as the baby's breathing, you're getting a changing magnetic field because the size of the loop is changing. That's the way it's designed. So the amount of flux going through that loop is going to change simply because it's getting bigger and then it's getting smaller. It's getting bigger and then it's getting smaller. So in the end, what that produces is a current that goes in one direction and then the other direction, one direction and then the other direction. As long as the sensor sees that changing current, it knows the baby's breathing. If at any time the baby stops breathing, well, then that loop will stop changing size. At that point, the current goes to zero. It sounds the alarm. And so that way the parents know, wait, the baby stopped breathing. We need to come and take care of it. And one of probably the most fun cases is the electric guitar. An electric guitar produces current. You're not actually hearing the vibrations of the strings. I mean, if the guitar is not plugged into an amplifier and you plug it, sure, you can hear that vibration with the string. But that's not actually what is being sent through the amplifier. As that string vibrates, then the pickups that you see that we've highlighted here on the end here, the pickups here are basically magnets. And so the flux that's going through those changes as the string vibrates. That induces a current. And it's that induced current then that's being fed to the amplifier. The rate at which that current changes then is exactly the same as the rate of vibration of the string. And so you get the same pitch because the amplifier is connected to a speaker. The speaker has a magnet, an electromagnet basically. And so as the strength of that current through the magnet changes, it causes the speaker paper to be attracted at different rates. And as that paper moves, it vibrates the air, and that's what produces the sound. So an electric guitar is also a direct application of Faraday's law. One of the very useful things that we can have with this, and you're going to see that used in a lot of applications. It's a great and powerful tool that we can use for constructing things that we just use every day. All right, so now you've seen how Faraday's law shows us how we can induce a current. And most of our modern world, from a mechanical sense, operates on this. This is how we can generate electricity. So if you have that coil moving inside a magnetic field in such a way that the flux through that coil changes, that's going to create a current. It's going to create a voltage that you can then use to power any kind of electronic devices or electrical devices that you want. We've also seen, though, that it's got very powerful uses in sensors, the baby monitor, ground fault interrupters, the electric guitar. The number of applications for Faraday's law are really endless. And so it's one of the most important things you want to keep in mind when you're trying to design these new devices for this. If you need a current that's produced, you can use Faraday's law to figure out what it's going to be. Okay, we'll see you next time.